Hello. Thank you very much for having us today, and it's a great pleasure to talk to you today about the advanced use of remote sensing tools for phenotyping. This presentation is made by myself, Nicholas Coops, Francois Detroit, and Samuel Grubinger. We're all based in the Faculty of Forestry here at the University of British Columbia. As I'm sure all of you are aware, tree improvement is critically important for us to improve the economic value of the planted forests. Here in British Columbia, a lot of our tree improvement is focused on coastal Douglas fir, one of the most commercially valuable species we have in British Columbia. The steps for tree improvement are well known. The first one is to assess our breeding values, which can be often expressed as volume or height. And once we have these breeding values, we then go and test the performance of those by planting trees, eliminating the tree interspacing, and assessing their growth over time. The assessment of the growth over time, however, is very difficult to do. Measuring the DBH and height of trees can be very time-consuming and expensive, especially if we do this over a period of time. Trees are very large, making estimates of things like height quite challenging. And ultimately, because we care about volume, we need to use allometric relationships to convert DBH and height to volume, which also covers some error. So as a result, new technologies to help us understand how to measure these trees over time would really help our tree improvement programs both in British Columbia and globally. We've seen a real revolution in the way we can apply technologies to help us do this. And these technologies, remote sensing based, can be focused on technologies like LiDAR and digital photogrammetry, which can improve our understanding of the structure of the trees, as well as spectral information, which gives insight into the functioning of the foliage itself. I'm sure you're familiar with these technologies, so I'll move through them quickly. LiDAR is a laser pulse. That laser pulse is fired down to the ground and builds up a three-dimensional point cloud of the tree structure. We can get to see information about height, but also, as we'll see during this talk, information about branching, which can be very useful in terms of the competitiveness and the growth of an individual tree. Using LiDAR, we can build up tree-based information, which can also be summarized to a stand, providing information on stand structure. Digital photogrammetry is where we take many photographs and we use different angles to build a three-dimensional point cloud, like LiDAR, but based on photography. It doesn't give us the complete three-dimensional structure because we are limited to just the tops of the crowns that we can see, or the ground if there's a gap. But these point clouds provide spectral insights and are also cheaper to acquire than LiDAR. The third data set that we're starting to see also use more is spectral information, focused on the chlorophyll and the near-infrared parts of the spectrum, as well as other narrow bands, which gives insights to other pigments. These can also provide key insights into the functioning of the forest. These technologies can be put on planes, in some cases satellites, but often a new technology that we're using is drones, or remotely piloted airborne systems. These systems allow us to collect much more fine resolution imagery than ever before, but also allow us to fly much more often, depending on when we want to fly, to go and build these data sets. Together, they're really revolutionizing the way we measure our forests. I'll now move to Francois, who will talk about our studies that we've been doing in British Columbia using these data sets.
Realized gains trials are used to test predicted gains and simulate what happens when we grow trees of similar genetic stock at operational densities. In Douglas fir, we have 3 genetic variations planted at 4 different spacings. Here we can see an example of some LiDAR data with the wild stand, which is unimproved trees, mid-gain, which represents a 10% volume gain, and top cross, which represents an 18% gain. There's 2 main approaches that we use to analyze these trials. One's an individual tree-based approach, one's an area-based approach. In both approaches, we create metrics where we try to identify differences between the genetic levels. We know that the trees of similar heights have crowns that move upwards, and when they're planted at wider spacings, the crowns lengthen, but we don't know whether there's differences between the top cross trees and if they behave differently to the mid-gain or the wild stand trees. For the individual tree approach, we first need to segment the trees before we can go away and take these individual trees and create metrics such as Weibull probability density functions and also crown volume functions. The Weibull probability density function is very useful because you can easily summarize the foliage profile using just the scale and a shape parameter. Here we can see what happens when we increase the scale and the shape parameters on the left and the right. The interaction plots here show that there are differences between the wild stand trees and the top cross trees, both for the scale and the shape parameter, which means this is a promising metric that we can use. We can also see how these foliage profiles vary for the top cross and the wild stand trees, and how there's a lot more variation with the top cross trees compared to the wild stand trees. This ability to produce different physiological phenotypes in response to environmental conditions is known as phenotypic plasticity, which is a desirable trait in these trees, and we want to plant trees that have this trait. The next approach that we can look at for the individual trees is to go down to the branch level. This is when we only characterize the upper third of the crown, and we use a clustering approach to build our branches and go in and then do a PCA to look at things like length, width, branch angle, and volume. We found that for these metrics, the top cross trees at the 4-meter spacings were all consistently significantly different whenever genetic level or the interaction effect was significant. One thing to keep in mind is we found that the interaction between genetic level and spacing was consistently very important, and so it's always important to take this into account when we're trying to make these comparisons. And now I'll pass it on to Samuel, who will talk about some area-based approaches and future directions for our research.
So Francois has talked a bit about the tree and branch level approach, but we can also analyze these types of trials at the stand level, and that allows us to analyze some attributes that don't necessarily manifest in individual trees, such as leaf area, density, percent cover, and these volumetric approaches that allow us to describe the spaces in between trees as well as the trees themselves. My initial work is focused on leaf area and leaf area proxies, which we can produce from point cloud data using the percent of points that make it through the canopy adjusted for their scan angle. And when we validate those proxies against traditional methods of estimating LAI, we get quite strong results. And at the plot level, we also see that height results are strong as well. A simple model combining realized genetic gain calculated for this leaf area proxy at the stand level and realized genetic gain for height gives us very strong results that closely track the realized gain in volume that we're targeting. So I'll talk a bit about what's next in this process and these technologies. A lot of my work so far has been around developing a phenotyping workflow. There are many different types of trials in British Columbia, and it's very important to be able to accurately combine data sets, delineate tree crowns, and extract meaningful data for a range of different trial types in different environments. So here we can see that we've combined both spectral data sets and structural data sets using a semi-automated tree crown extraction process to produce a variety of metrics from multiple data sets. This is PRI, the photochemical reflectance index, as well as a height and a crown area descriptor. And these metrics together give us a much greater volume of phenotypic information that can be used to analyze differences among families and populations. In addition to those different types of metrics, we can also look at temporal dynamics in a single metric. So we've undertaken a longitudinal study at a single site in the interior of British Columbia to look at the differences in spectral indices across time. So trees are not static in their foliage, and they react to drought stress, favorable conditions, and cold, as well as a phenological cycle. So the question is, can we use differences in reflectance over time to select differences in long-term viability for seed sources and families. So here we see the chlorophyll carotenoid index, which is an indicator of photoprotection in conifers. And we can see that as summer drought stress and winter cold progress, the values change. I've been working with a different set of trials in spruce. This is a provenance test, which is really aiming to quantify the effects of climate and climate change on different populations. And as you can see, there are profound phenotypic differences of the same populations planted at different sites, from warm, wet coastal sites all the way to dry, harsh interior continental sites. Having done several summers of fieldwork, we'd like to talk about some challenges that we have in British Columbia. Many of these sites are extremely remote, so while the acquisition of the data is quick, it often takes a lot of planning and expense to access these remote sites. We have to contend with the weather as well, so in addition to rain and lighting conditions, increasingly we have to deal with smoke, which is a problem for multispectral imagery. Validation data sets are very important in this kind of initial stage of testing a new technology. So it's important to find trials that have good validation data sets. And finally, tall trees are a big consideration for us. These sites aren't necessarily designed with drone-based remote sensing in mind, so the biggest limiting factor for us is really the tall trees planted around our sites of interest.
Okay, so we hope you've enjoyed this insight into the work we've been doing here in British Columbia. I think advanced remote sensing tools are clearly showing they can help inform phenotyping at a range of different spatial scales, from individual tree to the stand. The data that we can collect is robust and can be used over a period of time to actually see how these forests are changing, which provides additional insights. And the platforms we can use are also highly innovative, from drones all the way through to satellites. We welcome you to contact any of us to get more information about what we've been talking about today. We have a number of published papers, and we hope you've enjoyed this presentation. Thank you very much.